Welcome. I'm Eddie Rubin, Director of the JGI. Welcome to our 2011 Genomics of Energy Environment user meeting. The skinny of what's going to be happening the next few days. This evening we have fortunate to have two plenary talks. Persis Drell from SLAC and Terry Hazen will be giving plenary talks. Afterward, there'll be posters and food upstairs, an opportunity to meet with people from the JGI and users to interact. And I guess there's a no-host bar. Tomorrow, there'll be buses going back and forth between the JGI and here. Right after lunch, there'll be a user meeting. I'm really urging the users to come to this. And the purpose of this is the JGI is right now evolving a strategic plan for the future. We'd really like your input in getting directions and areas that you think we should be, the JGI should be in the next 5-10 years. Tomorrow evening, there will be buses from here to the JGI, which is about 20 minutes from here. And there'll be an opportunity to both see the JGI, there'll be posters there, as well as food. And so, okay, I'd like to introduce Persis Drell. Persis is the director of the SLAC National Accelerator facility and affiliated with Stanford in Palo Alto. Persis grew up at Stanford on the campus almost. She was in the company of physicists. She managed not to be derailed and head towards biology, but stayed true to the course and became a physicist. She got her PhD in Berkeley in atomic physics, went to Cornell University as a faculty member doing particle physics, eventually came back a little more than a decade ago to Stanford and joined the faculty there as a professor and became director of science at SLAC. Persis has many awards and honors. She's a member of the National Academy. One of the, I've heard stories recently, and one of her great accomplishments, as far as I'm concerned, is her ability to communicate and reach common ground with Tea Party congressmen about science and the role of science in the future, which is really quite important. We need people that can communicate. And so the question is, Persis is an accelerator physicist, from a lab that is famous for this, and we're a bunch of genomicists. And so why is she speaking to us? And so I think it's two reasons. One is that SLAC is a multi-program lab, and so biology is part of their agenda. And then also, as scientists, we need to make important discoveries. Frequently involves the application of new technologies. And SLAC, with their focus on intense beams of light to elucidate and understand matter, genomes, and the products of genomes is their target. And so it's a real pleasure to have Persis here.
Thank you. Okay, thank you very much. So, this story starts on Friday, April 10th, 2009. It was 10 o'clock at night. The phone rang. I was sound asleep. Lab directors go to bed early on Friday night. And the voice on the other end of the phone, as I was struggling to wake up, said, "We have a laser." And with that, the era of X-ray lasers at SLAC, the Linac Coherent Light Source, LCLS, had begun. As is often the case with major technological innovations, the seeds for that late-night jubilant announcement had been planted 15 years earlier. A very smart accelerator physicist, Claudio Pellegrini at UCLA, with some really good ideas and a vision, had come up with the concept that you could use what was then the 40-year-old and is now the 50-year-old linear accelerator at SLAC to make the world's first X-Ray Free-Electron Laser. And so now, some years later, it came into reality. So I'm going to talk about the Linac Coherent Light Source, which is the world's first X-Ray Free-Electron Laser. But I think I better start with telling you why we should be interested in X-rays. So what are X-rays good for? Well, there's two properties that we like about X-rays. One of them everyone is familiar with because you go to the dentist or you go to the doctor, and that is that X-rays penetrate, so you can see what's inside of material. And then the second property is because the wavelength of the X-ray is very, very short, it lets us see structure on the atomic scale. Where are atoms in materials? Where are the electrons in the material, very important for the properties of the material. And then if you want to get sophisticated, they can even tell you, X-rays can even tell you about the spins of the electrons in materials. Now, intense beams of X-rays from synchrotrons have been around for several decades, have caused a revolution in structural biology. But there's a new generation of X-ray sources coming into being now. The current focus is not so much on using X-rays to determine structure, because we've been doing that for decades. It's dynamics. It's can we use X-rays not just to see where the atoms are, but can we see what the atoms are doing on the time scales that atoms are doing things interesting. And for your reference, because it's going to come up again and again in the talk, that's the time scale of femtoseconds. So can we have X-rays that will give us dynamical information on the femtosecond time scale? Turns out there's actually two technical options. One, an energy recovery LINAC, is in development at Cornell and other places. But the technical option that's gotten to the goal line first is the idea of using a free electron laser. And as I say, the first X-ray free electron laser has just come into operation. So I'm going to spend a few minutes, because I'm a physicist and I can't resist, telling you how the free electron laser works, but I'll do it at a really high level. I'll tell you a little bit about our LINAC coherent light source and its early performance. And then I'll tell you about a few of the early experiments at LCLS which have the potential to have really profound impacts in biology. And I'll end with a look forward, because we have just started to open this frontier, and I don't think we know where it's going to take us yet. So the first thing I always have to say when talking about how a free electron laser works is it's not like a normal laser. Remember, laser stands for light amplification by stimulated emission of radiation. The process of radiation generation is very different in a free electron laser, but the radiation product, what comes out, boy, it's laser-like. It's intense, it's coherent, and so, you know, the purists can argue, should we call it laser, should we not call it laser, but it looks like a laser, it walks like a laser, you get it. Okay, how do you actually generate that very intense radiation? Unlike a synchrotron, which if you've got any experience with intense beams of radiation for structural biology, most of that work is done at synchrotrons. There you have electron bunches running around in circles. For a free electron laser, you actually accelerate the electrons in a linear accelerator, which is just what it means. It's an accelerator in a line. So you accelerate the electrons in a line. That allows you to make very, very short electron bunches. And that short electron bunch is what's going to give you a very short X-ray pulse, which is how you're going to get the dynamical information you want. So the downside of this scheme is that you use that electron bunch once and you throw it away. With a synchrotron, you can keep milking the electron bunch for its X-rays for hours. But anyway, so for the free electron laser, we take this very, very short, and by very, very short, I mean micron-sized bunch of electrons, and maybe it'll have 1 billion electrons in it, and you send it through a very long undulator. What do I mean by very long? I mean 100 meters. I mean the length of a football field, okay, of undulator magnets. The undulator magnets wiggle the electron bunch up and down just by microns on its orbit, but that's enough to cause the electrons to radiate X-rays. That's what charged particles do when you accelerate them. The X-rays generated from the back of the bunch start to impact the front of the bunch of the electrons. There is a self-interaction, and it orders the electron bunch, and that electron bunch starts to radiate coherently. And that's the source, then, of this very intense, coherent radiation. The one thing I've learned about free electron lasers is it's all about the electrons. If you can have the beautiful electron bunch, you can make the X-ray laser work. And so what do you need from your electron bunch? You have to have an extremely bright electron beam. It's got to have very high peak current, low emittance. That means very small, all those electrons in that micron-sized bunch are packed into a very small part of phase space. And in fact, the performance depends exponentially on the electron beam quality. But that was good for us at SLAC, because our history was for 50 years making beautiful electron beams. For the LINAC coherent light source, we have a 3 kiloamp electron beam to generate the X-rays, and that translates into 6 billion electrons stuffed into a 30-micron sphere, just to give you a picture. Free electron lasers have been around for a long time. The first one was operated in 1977. They have been used in the infrared. They've been used in the visible. Before the LINAC coherent light source turned on, the shortest wavelength was a machine called Flash at DAISY, which went from 6.5 to 50 nanometers. The design goal for LCLS was 1.5 to 15 angstroms. One comment I'd like to make, or I can't resist making, is that through this history of several decades, free electron lasers have earned a very well-deserved reputation for being finicky, difficult to operate, temperamental machines. The design parameters for LCLS were to go from about 830 electron volts to 8.3 kilovolts. So on the hard X-ray end, our pulse length was 230 femtoseconds, and now you immediately might say, wait a minute, you said you were going to talk about femtosecond dynamics. 230 femtoseconds is 2 orders of magnitude away from a femtosecond, but it'll get better. And our design was a pulse energy of up to 2 millijoules. So here's just a little quick animation of how we actually make the X-rays. The SLAC LINAC, the klystron gallery, is what's up on the surface. We pipe an ordinary laser beam down to the about 40 feet below where the accelerator structure is. There's a photocathode, and this ordinary laser pulse, actually it's not that ordinary, but it's in the visible, kicks off the bunch of electrons. And right from the beginning, we have to worry about that bunch of electrons being very short and being very low emittance. We pre-accelerate the bunch of electrons and then stick it into the main SLAC LINAC about 1/3 of the way along. We actually don't have to use the full 2 miles SLAC LINAC, which I'll show you a picture of in a minute. We use 1/3 of it. We have 2 chicanes. That's just a trick that we use to shorten the bunch. We put a chirp on the electron bunch, and then the chicane allows us to compress it. We have 2 of those, and then we accelerate the electrons from their initial energy, which was not much, up to as high as 14 GeV. The energy of the electron is what's going to determine the wavelength of the X-rays coming out. So this is kind of boring. You accelerate the electrons. Now you go into a drift space, which was really for convenience more than anything else. And then after the drift space, you go into the undulator hall, and that's where the magic happens. The undulator hall has to be temperature controlled, stabilized, because you're going to put these electron bunches through 100 meters of undulator. They have to stay phased and aligned to well better than a micron over that 100 meters. The electron bunch gets wiggled up and down by the alternating poles of the undulator magnet. It starts to generate a radiation field. The radiation field starts to interact back with the electron bunch, and the entire bunch starts radiating as one, and that's where the coherence comes from. So at the end of the undulators, you have a very well-ordered electron bunch that's radiating in this coherent fashion. The electrons and the X-rays you've generated are traveling along together. You now have to get rid of the electrons. We don't need them anymore. So at the end of the undulator hall, there is a big magnet that bends the electrons down into a dump in the ground, and the X-rays stream free. By the way, at this point, from where the gun of the electrons was to here, we've gone almost 2 kilometers. Things like the curvature of the Earth are a big deal because X-rays, they go straight. Okay, they don't care about the curvature of the Earth. That ended up to be a significant factor in the construction. Then we go into, the X-rays go into 6 experimental hutches, 3 in the near hall and 3 in the far hall. Not all of these experimental hutches are complete. At this point, 4 of them are either operating or commissioned, and 2 more have to come online. So this is what it actually looks like, not in cartoon form. The Pacific Ocean is over here. These are the foothills skyline. San Andreas Fault is running right about here. You have the 2-mile-long SLAC LINAC, the 50-year-old SLAC LINAC. This is Freeway 280. For those of you who drive south of Sand Hill exit on Freeway 280, you drive over the SLAC LINAC all the time. The LCLS injector is here at it's foreshortened, so that's 1 kilometer from the end. Here's the drift space. The undulators are under this hill, the near haul and the far haul. A more direct overhead view shows this is the undulator tunnel under the hill. The near haul is above ground. Actually, the far haul is totally buried and you can't see it. This is what the undulator haul looks like. That, for me, is just a beautiful picture. Those 100 meters of undulators. The first electron beam came through this hall in December of 2008. We installed our first undulators in March 2009, and first lasing was April 10th. None of us expected that rapid of a turn-on. When you're going to turn on a new machine, you say we have the lasing campaign for the LCLS, because we thought it might take a few weeks or a few months, and we wanted to manage expectations. So we started the lasing campaign on April 10th. And you can see this is Paul Emma, who led the commissioning team, in the control room. This is John Golida, the project manager. What they did is they put undulators on the beam one by one, and then when you had a certain number of undulators, the hope was you might see some amplification of the radiation, and what they saw was lasing almost instantly. So they're all very happy. And then, as I said, we'd all been conditioned to think that this was going to be a finicky, temperamental machine. But they went home about 11 o'clock that night. They just put the stopper down on the electron beam. They came back the next morning. They lifted the stopper, and it lased again. And it's really just not stopped lasing since. The turn-on surprised us in more ways than just its speed. This is a gain curve showing the power out of the free electron laser as a function of length along the undulators. Told you we had 100 meters of undulator, but you saturate after about 60 meters. Turns out we had 50% or 30% more undulators than we needed because the emittance of the beam was better than we expected. So we were very rapidly getting over a millijoule. The pulse started out shorter than we expected, 100 femtoseconds, and very quickly the accelerator physicists figured out a way using very small bunch charge to get down below 10 femtoseconds. So we are able to routinely run with what we believe is sub 5 femtosecond pulses, but we don't have a good way of measuring the X-ray pulse at that length. So we're just having to rely on the simulations and the time structure of the electron bunch, but it's very hard to make an X-ray pulse that's longer in time than the electron pulse. And there are active strategies being developed to actually measure that pulse width. We're very interested in it. This was the baseline performance that I told you about that we expected. This is what we currently get now, 2 years later. We've been able to go down below the oxygen K-edge, and we've been able to go up to 10 kilovolts. The pulse length, we aimed for 230 femtoseconds. We routinely can change it between 5 and 500 femtoseconds. And we were hoping for 2 millijoules, and we've run now up to 4 millijoules. You don't get all of these parameters all at the same time, but probably the most important one is that around 70 femtoseconds, which is an important pulse width, because when we take images of things that we destroy and they explode, if the pulse width of the X-rays is shorter than 70 femtoseconds, we actually beat the explosion, and so you actually get a crisp image, diffraction image, before the thing blows up. So it's a fast strobe, if you will. And sub 70 femtoseconds turns out to be the speed of strobe we need, and we've been able to get close to 4 millijoules at that pulse width. So this is just a reminder. The real experiments go on in the near hall and the far hall. There are 6 of them. When we first turned on the LCLS, actually, when it first lased, it lased at 1.5 angstroms. You would have thought we would have started at 15 angstroms and then worked our way down to 1.5, because everything gets harder as the wavelength gets shorter. All of the tolerances get tighter. The alignment gets more critical. But as is often the case, all of our diagnostics weren't ready when we were ready to test out the lasing. And so we ended up trying the lasing at the very short wavelength end, because the diagnostic we could use was a nickel foil. Nickel has a K-edge right around 8 kilovolts, and by the transmission and absorption through the nickel foil and the sharpness of that, we could actually determine whether we had lasing or not without the other suite of diagnostics, which was still to come. So we first lased at 1.5 angstroms. But the first experiments we ran were designed for longer wavelengths. So the first experiments were done at 10 to 15 angstroms in the atomic, molecular, and optical hutch, the first hutch. The second hutch, which turned on in May of last year, was specifically a soft X-ray surface experiment. Then in October of this year, we started our first hard X-ray experiment in hutch 3, where we actually did experiments at 1.5 angstroms. And then just in December, we started commissioning the X-ray coherent imaging, which is for technical reasons in hutch 5, and we got some very good results from a user run there in February, which I'll tell you about. We have 2 more experiments to turn on. Both of them should turn on in fall of 11. Just to put in a plug for ARA funding, these were much more strung out and dragged out in terms of when they would turn on because of the original funding profile of the instruments. But with the ARA funding, that was one of the targets for ARA funding from Office of Science. So we got all of the money last year or the year before, and then we're able to go on a technology-limited schedule and really pull the schedule up, which turned out to be a good thing because everything was moving faster than we had anticipated. So the first 2 years of LCLS is very exploratory. This is a new machine. We have dynamical information on timescales we've just never had before. We have brilliance of the pulse that is many, many orders of magnitude higher than anyone's ever handled before. So you have to learn how to do experiments. It's not obvious at the beginning, and particularly, you constantly have to ask yourself, am I actually seeing physics, or am I just seeing that I'm damaging my sample? Okay? So the first round of experiments are largely proof of principle. We award beam time on a proposal review process, just as all other facilities in the Office of Science. Typically, we are getting 5 times as many proposals as we can schedule, which is not a good thing at a certain point. People get tired of writing proposals and having them turned down. We've done a few forced marriages where we have groups with similar types of science where we've said, if you guys will work together, we'll give you beam time. If you can't work together, nobody gets beam time. That's worked surprisingly well. But we're trying to maximize the number of user groups and the diversity of experiments in this first 2 years as we're turning on the different end stations to do different science. We don't have program proposals now, but we will move to that because once all of the end stations are operating, the new fields that we've opened are tested, we need to start to identify and invest in the science areas where the LINAC coherent light source, where this X-ray laser is going to have critical impact. And so we'll start to schedule more strategically. We do have competition coming. There is a machine in Japan that they've just turned on the linear accelerator part, but will ultimately make X-rays as a free electron laser. And the really big machine is at DAISY in Germany, and their X-ray laser should start commissioning in 2016. So we have sort of a period where we own this frontier, then others will join. That's fine. There's a ton of science here, but we want to have fun while we own this frontier. So I'm now going to talk about the strategy behind 2 experiments that were done early on and have actually been repeated since. I can't give you the latest results because we don't have them yet, but I can give you the early results and tell you sort of what they're seeing with their second runs. This is a class of experiments that I hope might be particularly interesting to you, where one wants to start to think about doing atomic resolution scale imaging of biologically interesting quantities, whether it's single molecules or nanocrystals or whole cells. It's take biologically interesting materials and can we image them in this facility in ways that we couldn't do with the synchrotron. So now remember, we've got this X-ray laser that's pulsing at 120 seconds, 120 times a second. We get 1 pulse, 1 measurement. So you have some strategy to inject particles. And back in 2000, the image was that, or the thought was, you would drop particles in, you'd hit them with the X-ray laser pulse, you'd get a diffraction pattern, and then the thing would blow up. You'd get a noisy diffraction pattern. And then the question was, could you combine a bunch of noisy diffraction patterns to actually be able to get something that would allow you to reconstruct the structure of the particle? Once that was established, Then there were things you could start thinking about doing ultrafast dynamics, initiating a reaction at different times before you hit it with the X-ray laser. Your imagination can just expand, but there was just a critical question was, would this concept work at all? So again, just to have a little video of how it happens, you drop your particles one at a time, you hit it with the X-ray laser beam, you capture a noisy diffraction pattern, and somewhere offline you combine all those noisy diffraction patterns and mathematically invert it to reconstruct the structure of whatever it was that you dropped into the beam. So, does this work? Well, let me remind you of the power of X-rays in structural biology. Crystallography has been done for decades at synchrotrons. The first step is the hardest. You've got to take your biologically interesting molecule and make it into a crystal. Once you've done that, you can get a diffraction pattern at a synchrotron, get the electron density map and the atomic model. The bottleneck is growing crystals large enough that you can actually get a signal at a synchrotron, and about half of the biologically interesting things we'd like to study simply don't make big crystals. Well, one of the early experiments at the LCLS was to say, gee, it's hard to grow big crystals, but growing little crystals is easy. And can we take little crystals and put them in the LCLS beam, and is the beam so intense, perhaps, that using this diffract before destroy concept, we can actually get the structure from a nanocrystal before we blow it up. So this paper was published in Nature. You'll notice the large number of authors. This is something that's starting to happen on LCLS as the teams are larger. These are complex experiments using lots of institutions. They had actually a water jet as opposed to dropping nanocrystals one by one. The whole technology of the microjet was actually kind of fascinating. But the idea was to get single pulse diffraction from photosystem 1 nanocrystals. That's something where we know the structure. It took a decade before people could make a crystal big enough that they could determine the structure of photosystem 1 at a synchrotron. Here, the nanocrystals were just everywhere. We were running at the long wavelength end because the first experiments turned on, remember, at the long wavelength end. And so you can't get better resolution than the X-rays you put in. So these were about 10 angstrom X-rays. They used different pulse widths. They collected a huge amount of data, 5 terabytes a night. The typical experiment this is what it looks like. The LCLS beam goes through here. The water jet is into the page. You have some near detectors and far detectors. The near detectors get the wide angle diffraction. The far detectors get the small angle diffraction. I think you can see it in this light. This is from the far detector. It's the small angle diffraction. You can actually see the coherence fringes. So this is a screenshot. I walked into the control room when they were taking this data, and these are just going up on the screen shot by shot as the laser fires. Now the laser at this point was firing at somewhere between 5 and 10 hertz, so they could put each one. When we now run at 120 hertz, they sample. But these are just raw data. And for those of you who remember Young's double slit from your physics experiment, you're actually seeing the double slit effect of the size of the unit cell of photosystem 1 and the fact that it's in a finite-sized nanocrystal, so you can count those fringes and actually get the size of the nanocrystal. It's really cool. This is what the wide-angle diffraction patterns look like. They were clean enough on a single-shot basis to be able to index them with standard indexing patterns from the synchrotron toolkit of software and combine into a 3D diffraction pattern. They were able to reconstruct the photosystem 1 with 8.5 angstrom resolution compared to what you would get from a synchrotron if you truncated an 8.5 angstrom resolution. So now you're going to sit there and you're going to say, so what? You measured photosystem 1 with 8.5 angstrom resolution, and I can take it to any synchrotron in the country and measure 3 angstrom resolution. Well, first, it was a really cool demonstration that this diffract before destroy works. But what I can't show you the data on yet is that in February, we ran this same experiment with the short wavelength X-rays, with 1.5 angstrom X-rays. And you see diffraction patterns with sub-2 angstrom resolution from the nanocrystals, which is better than you'll get at a synchrotron. It's worked spectacularly well. So what have we learned? Well, femtosecond nanocrystallography seems to work. It opens up a route for small or radiation-sensitive structure determination where you can't grow the crystal. We have very high-quality diffraction patterns being collected at the pulse rate of LCLS, and now down with the hard X-rays at the 1.5 angstrom with very good resolution. This diffract before destroy works. You can immediately extend this to femtosecond time resolved measurements of photoinduced dynamics. And in fact, those experiments, they've already been starting to do those. I just don't have results to show you yet. And I think we all think we're seeing the first killer app of the LCLS. If it does nothing else, it will do this science. But we intend to do a lot more. So the second paper that was published in February that's gotten a lot of attention was based on 3 hours of data taken Christmas a little over a year ago, when the group that did the nanocrystals had had such terrific success that they were running out of other samples. They'd finished all their nanocrystals. And for the last 3 hours of running, Janusz Haiju, who'd been pushing this for a long time, said, I want to put in something the size of a cell and see if I can get single-shot images of a cell. Now, this is a whole lot harder to do non-periodic imaging because a cell isn't a rigid body. So you're going to get one shot of a cell, and then the next pulse is going to get another shot of a different cell where everything's been rearranged. And so the critical question, and we don't know the answer yet, is can I get enough information on a per-shot basis that I can actually combine subsequent shots, perhaps putting in some assumed knowledge of where things fit. Maybe I can get clever and tag a few things along the way and have a laser beam crossing it. This is really the first step of something that we don't know if it's going to work or not, but boy, if it works, it's exciting. Again, very big team. They chose the Mimi virus because you cannot crystallize this thing. It's got these funny little hairs around it, and it's big. Okay? It's 0.5 micron. Again, they had a jet of Mimi viruses intersecting the X-ray beam. You could go in the control room and see these diffraction patterns in real time. And these were just 2 of the diffraction patterns they got in that 3-hour run. These are the first reconstructions. This is now to compare with what you can get on the Mimi virus from cryo-EM, where you have to slice it. So we're doing better than cryo-EM, but it's still not clear there's real information in there yet. This was again done with long wavelengths, but that's probably where you'll stay with here, because you don't really care about where the atoms are so much as the bigger structures. They typically had 30 nanometer resolution. They had some trouble with their detector. There were saturation effects. They did a run in February where they got, I'm sure, several million shots. So the analysis of that data will tell us whether there's science here. But already we see in a homogeneous interior structure that is different shot to shot. Whether we'll do science with that or not, it remains to be seen. So what have we learned so far? And then I'm going to wrap up. There's a whole lot of other science that's going on at the LCLS. Not everyone at the LCLS is a biologist, it turns out. But I thought I would focus on those applications for this audience. We can take a neon atom, we can strip every electron off it and watch it reassemble. We can take a neon atom and we can take the 2 core electrons out and watch what it does when it's trying to figure out that its core electrons are missing. The probe before destroy opens the door for imaging of nanocrystals and nanostructures. That works. That will be an industry for the X-ray Free-Electron Laser. Single-shot imaging of individual viruses and cells. Well, the concept seems to work, but major improvements are needed before this is science. We've also been doing single-shot spectroscopy and imaging of solids and surfaces. The biggest thing we've learned is the demand for the beam and people wanting to do experiments is outstripping our ability to deliver the beam by a factor of 5. So what's next? Well, for LCLS-1, as we now call the machine we have, but that's because there's an LCLS-2 coming along, we've done the nanocrystal imaging now at 9 kilovolts. I can't wait to see that analysis because the sub-2 angstrom resolution on the nanocrystals, as I say, will spark an industry. We've got the several million shots of Mimi virus. Will that non-periodic imaging work? By the way, if it works for a single mini-virus, can you make it work for a single protein? Do you even need a nanocrystal? Can you actually, do you have enough photons that you can think about imaging single biological molecules? Not clear. We don't know the answer yet. And then we're starting to do something that the chemists, the femtochemists, are extremely excited about, which is femtosecond resolution movies of chemical systems in action. You know, put an oxygen atom on a surface, watch it come off, watch it bend. Those experiments are starting. We have ongoing R&D to make the LCLS pulses prettier. Right now, we're essentially amplifying noise. We'd like them to be transform limited. There's a really clever technique that makes several femtosecond pulses, about 150 femtoseconds apart, so you can do pump probe. We can add bunch trains. We're looking at multi-use beam multiplexing and splitting. And then we have the desired extensions to LCLS1, which are making up LCLS2, which is actually already started in the DOE parlance. We got CD0 for LCLS2 about a year ago. It was kind of cute. The same day we got the CD4 milestone for LCLS1, they signed the CD0 for LCLS2. We have our CD1 review for LCLS2 coming up. And the goals will be extending the spectral range down to the carbon K edge, going to harder X-rays, so you can do mad phasing with selenium. Shorter pulses, sub 1 femtosecond. And by the way, we better be able to measure what the width of the pulse is by the time we start going sub femtosecond. Polarization for people who want to look at charge and spin effects and materials. We'd like to control the pulse better, and there's various ways of doing that with techniques called seeding, where instead of amplifying noise in the electron bunch, you actually seed the X-ray generation with a seed pulse. We'll actually do an experiment on that this summer, but really full-scale deployment of that would wait till LCLS2. And then capacity. We've got to increase the capacity. The LCLS2 will be if this is the LCLS1 tunnel in the near hall and the far hall, LCLS2 is a second tunnel. We use actually another third of the SLAC LINAC because we're only using a third of it for LCLS1. We've got 2 more thirds to go. So you might imagine there's going to be LCLS2 and LCLS3, which would give us the full capacity of the site. At LCLS2, we will take this middle third of the LINAC. We'll have the capability for 2 more undulators, 4 more experiments. We also have the capability to put a second undulator in the current LCLS. So ultimately, what we want is 3 injectors. We'd like them each up to 360 hertz, 4 seeded undulator sources, 10 experimental stations. And I still think that demand will outstrip availability, but at least you'll be able to move a little faster in terms of discovery science. So the near term is very exciting. LCLS1 is in operation. And I have to say, it's operating with a capability that we did not dream of before it turned on. It's really been quite an experience for the lab to have something turn on this fast, this spectacularly. And it's almost as though the machine is leading us. LCLS2 is moving forward. We're adding capability and capacity, much of which we couldn't have even dreamt of before the thing blazed. Certainly this idea of going to the very short pulses, every user that's come has wanted to use the short pulses. And you can actually understand why. That's the simplest way to see if you're damaging your sample or not, is you keep making it's the long pulses you're going to be damaging your sample, and so you just keep reducing the size of the pulse width until you see the damage go away. We really feel a new scientific frontier has been opened. We're going from structure to dynamics at the femtosecond scale. And I think all of us think that the biggest surprises are yet to come. Thank you. Getting the phasing because it's actually longitudinally not terribly coherent. It's transversely very coherent. So
you still need then some kind of...
So the answer is we don't yet know. If you take a close look at that diffraction pattern I showed, you see diffraction fringes. They have to be telling us something, but we don't know if it's telling us enough that we can avoid all those other tricks that are standardly used. We don't know the answer to that yet.
So when you use also the microcrystals injecting, can you actually maybe do gradually advancing microcrystals because your time is so short?
If I think I understand your question, what we certainly could do, we think, is trigger a reaction
Yeah.
and then change the time delay between when that reaction is triggered and when the LCLS images the nanocrystal.
Yeah.
And that sort of pump probe we're set up to do. We can lock a laser to the LCLS pulse and then vary that time distance. Is that what you're,
No,
so for
no,
pump probe?
Just mechanically, if you have small crystals, they're easy to make.
Well,
Tiny crystals are easy to make.
nobody even yet knows how many gallons of nanocrystals they throw down the drain because they've never looked at them before. But so far they seem quite easy to make.
If you align the nanocrystals like this, and then you let it advance very slowly compared to the time scale of the beam, then even though you're damaging advanced part.
Oh, I see what you're saying. It's like a raster.
Yeah.
The raster. So we do some rastering because the time between subsequent X-ray laser pulses is long. It's 120 hertz, gives you lots of time between them. So yes, we do some rastering, not so much on crystals. The nanocrystals, it's easy to just blow the thing up.
Very exciting.
Yeah. Other questions?
So what percentage of your users, biologists?
I think we have very few people that are card-carrying biologists because we're not going to see the biologists until the technology's worked out.
Right.
And so the Chapman, Janis Haiju, that team, I'm probably insulting somebody. There probably are a few card-carrying biologists in those big teams, but right now I think we're really in technique development.
Right.
But certainly there are card-carrying biologists at Stanford who I didn't used to know, who now are very, very interested in coming up and doing experiments.
Okay, any questions for Persis? Well, thank you very much. That
Sure.
was great.